Hello, I'm Kulshar Ares from Mechanical Department of RV College of Engineering. So, regarding robust design subjects, experiential learning, I took the topic about Taguchi optimization of solar PV power output. So, I will be explaining about how to actually analyze the Taguchi optimization of solar PV power output using the Minitab software. So, to give a brief introduction about my analysis, so the study applies the Taguchi method to optimize solar PV power generation. So, we analyze the effects of three factors at three levels. So, the three factors which I took was tilt angle, that is 15 degree and 13 degree and 45 degree, and the sunlight intensity which is represented in Weber per meter square is 600, 800 and 1000. So the temperature which is in degree Celsius is 20 degree, 30 degree and 40 degree. So I used here, we use the L9 orthogonal array to minimize experiments and while maximizing the insights. So basically, now we should see that how what is the solar panel and how it works. So basically, a solar panel is a device that converts sunlight into electricity by using photovoltaic cells. So PV cells are made of materials that produce excited electrons when exposed to light. So these electrons flow through a circuit and produce direct current, which is also called as DC electricity. So which can be used to power various devices or to be stored in batteries. So the solar panels are also known as the solar cell panels, solar electric panels or PV modules. So now we will see how actually the working principle of the solar panel. So the working principle of a solar panel revolves around the photovoltaic effect. So which is an important effect which is essentially means converting light into the electricity. So here's the breakdown of the process. So in the first step, the photovoltaic effect is explained. So this effect occurs when a certain materials, primarily semiconductors like silicon, absorb sunlight. So sunlight is made up of particles called photons. When these photons strike the solar panel, they transfer their energy to the atoms in the semiconductor material. So basically, the semiconductor materials which are used in the solar panels are N-type silicon and P-type silicon. So in N-type silicon, this layer can excess will be having the excess of electrons, and P-type this layer has a deficiency of electrons, which will create holes. So when these two layers are joined, an electric field is formed at the junction between them. So the third step is generating electricity. When photons from sunlight strike the solar cell, they knock electrons loose from the atoms in the silicon. The electric field at the junction forces these electrons to flow in one direction, creating an electric current. So this current is actually called DC current, which is direct current. So the main step is converting DC to AC. So most homes and electrical grids use alternating AC called AC electricity. Therefore, a device called an inverter is used to convert the DC electricity from the solar panels into AC electricity. So the main applications of using the solar panels are, so first one is the residential application where we use at home like rooftop solar systems. Homeowners install solar panels to generate electricity, reducing or eliminating their reliance on the grid and lowering energy bills. So solar water heating, so where the solar thermal systems use sunlight to heat water for domestic use, and the solar lighting. Solar powered lights for gardens, pathway, and security will conserve the energy. So and moreover, it's a renewable energy. Commercial and industrial applications are solar farms, where the large scale solar power plants generate electricity for the grid, and the commercial building integration. Solar panels integrated into building roofs, facades, and parking structures. And the off-grid power is also where the providing power to remote locations such as telecommunications towers, oil and gas platforms, and remote monitoring systems. And solar panels can also be used for agriculture applications like solar water pumping, using solar energy to pump water for irrigation. Solar crop drying, like using solar energy to dry crops and agricultural products. Solar greenhouses, providing power and heat to control greenhouse effects. And other applications are space exploration, portable electronics, and consumer products like solar powered watches, calculators, and other small devices. So If we come to the analysis part, this is the L9 orthogonal array which I have used for the analyzing the system or what experiment what I am doing using the Minitab software. So in the first column it is the first factor which is the tilt angle which varies from 15 degree to 45 degree, and the sunlight which is represented in Weber per meter square is varies from 600, 800 to 1000. So then the third column says that the temperature variation, so it will be vary from 20, 30 to 40. Then the corresponding output which I have got by the three factors is for the power output which is represented in watts. Now we will see how this table can be analyzed in the Minitab software. So this is the main interface of the Minitab software. So first we will go to stat, then DOE, then Taguchi. So create Taguchi design. So here we are using the three level design up to 2 to 13 factors. So press on three level design, then number of factors is 3. So design says L9 3 into 3 columns. So press OK, then go to factors. In factors, my table which I showed in the PPT, first factor A is the tilt angle. So type the tilt angle. So second one is the sunlight. Third one is temperature. So the level values for tilt angle is 15, 30 and 45. For sunlight it is 600, 800 and 1000. The temperature varies from 20 to 30 to 40. So press click on OK. So here you can see the tilt angle, sunlight and temperature column has been produced. So another column is the power output. So we should manually type it. Power output. So that is first value what which I got is 135 Weber per meter square and so on. 120, 75, 90 and 60 and 225, 45, 45, 180 and 150. So we have the required data for the analyzation. So we'll again click on stat and go to DOE and Taguchi. Now we click on analyze the Taguchi design. So the response which I have taken is the power output. So power. So click on OK. Now you can the plots of the Taguchi analysis. Now you can also use this analysis for generating the ANOVA table also, like we can use the one-way ANOVA. So in the response, we will take the power output. In factor, I will select, for example, temperature. Now click on OK. So you can see the ANOVA plot, which is one-way ANOVA plot, which has been formed. You can also vary the factors which I have done for temperature. You can vary for sunlight and tilt angle, and keeping the power output constant. Now we'll go to the PPT. So this is the power output which I got conducting the experiment. So this is actually the signal to noise ratio calculations, which I have taken larger the better. So the corresponding signal to noise ratio, which is represented in decibels, is represented in the table. So now we'll come to the genetic algorithm explanation. So genetic algorithm is used for optimizing flow rate while minimizing the pressure drop and loss. The steps which are taken in genetic algorithm are initialize the population with random solutions. So then evaluate the fitness using the objective function and select the best candidates and apply crossover mutation. Then repeat for multiple generation until convergence is happening. Then this is the basic code which I have generated using the Python software. So here you can see the three factors which I have got, that is which I represent in the table. Then this is a small code. So basically, the observation which I made conducting the analysis and the experiment conduction is the highest signal to noise ratio is 47.04 decibels, which occurs at the tilt of 30 degree of the solar panel, and the sunlight intensity will be 1000 Weber per meter square, and the temperature correspondingly will be 20 degrees Celsius. So this, if we conduct the experiment in this above specification, the setting maximizes the power output, and opposite of that, with the lowest signal to noise ratio is 33.06 decibels, occurs at tilt angle 45 degree. The sunlight is 600 Weber per meter square, and the temperature is 40 degrees Celsius. This setting yields the least stable power output. So this is the least stable which I have got, and the Taguchi method effectively identifies the optimal conditions with minimal trials. So now we'll speak about roulette wheel. Roulette wheel selection, also known as the fitness proportionate selection, is a popular method used to genetic algorithms for selecting individuals based on their fitness for reproduction or the next generation. So this, now let us see how it works. First step, the fitness evaluation happens. Each individual in the population is evaluated based on its fitness. The higher the fitness value, the more likely is to be the selected for reproduction. And the calculate total fitness, you sum the fitness values of all individuals in the population. This gives the total fitness. Then the calculation of the selection probability. Each individual's probability of being selected is proportional to its fitness. For each individual, the selection probability is calculated as, so for example, pi is equals to the fitness of the individual of the total for all individuals. So then we create the roulette wheel. Imagine a roulette wheel is divided into sections where each section represents an individual in the population. The size of each section corresponds to the individual probability of being selected. Then the spin the wheel, a random number is generated which ranges up to 0 to 1. This number is then mapped to the corresponding individual by transversing the roulette wheel from 0 to 1. So the individual whose section contains the random number is selected. So the selected individual will be used to generate the next population. So these are the final conclusion which I did for my analysis of the solar power PV power output. So for maximum power output, the optimal combination is the tilt angle of the solar panel should be 30 degree, and the sunlight should be 100,000 Weber per meter square, and the temperature should be 20 degrees Celsius. So for future work can include testing additional factors like panel type, shading effects, and running real world validation experiments like using regression or machine learning for further insights. Thank you.